Hello, everyone. Thanks a lot for joining us. I'm Lydia Moreno from the Daylight Academy, and it's my great pleasure to welcome you to this third and last session of the Daylight Awareness Week. For this edition, we have undertaken a long and fascinating travel to follow light from the sun to the moment it reaches us on Earth. I'm so sorry, I have to ask if you hear me because I don't see me, just a short confirmation.
You're fine.
Okay,
yeah.
Thank you very much. So for this edition, as I said, we have undertaken this long and fascinating travel. And we start in the infinitely large, close to the sun on Tuesday. And we made then a stopover on Earth yesterday, and this gave us the opportunity to explore different roles, different uses of natural light on Earth in our direct environment. Today, to conclude our journey, we will dive into the infinitely small this time, and together with excellent experts, researchers, we will address different effect daylight can have at the molecular level. So the experts will join us in a few moments, but before, let me just share a few information with us. And first about what is the Daylight Academy, because it may be new for some of you. So can you see my screen, my slides?
Yes.
Yes, thank you. So the Daylight Academy is an international membership organization that brings together different types of actors, mainly scientists with very different backgrounds, but also architects, engineers, artists, and other professionals particularly interested in topics related to daylight. And it has been initiated and it is also supported by the Velux Stiftung, which is a foundation based in Switzerland that supports scientific research. And the main goal of the Daylight Academy is to encourage creativity and innovation in daylight research, of course, through this interdisciplinary approach. But another goal, very important too, is to disseminate the knowledge and contribute to more awareness about the importance of daylight. And that's why we are here today and this week. I also would like to draw attention to the fact that we have an illustrator with us today, Marina Roa. She will be doing visual harvesting, which means she will be drawing during the session and capturing the most important messages from our discussions with in a nice visual way. And now I turn to you in the audience. Your contribution is also essential so that we can have a real exchange. So I really invite you to be active during the session, to write all your questions to the speakers. And for that, please use the Q&A, the question and answer tool from Zoom. There you can write questions at any time. And if you want, you can also like other questions that you find particularly relevant. Please also have your smartphone close by if possible, because we will have a few questions for you too. We will even have a quiz at the end, you will see. And for that, we will use another tool independent from Zoom, so it will be easier for you to use the phone. And last information, please note that the webinar is being recorded and that we are currently live on YouTube. So now we can move on to the real subject, and I'm happy to introduce Bernard Verly, who will moderate this session. Bernard is a professor of aquatic chemistry at the ETH Zurich in Switzerland, and he is also one of the founding members of the Daylight Academy. Bernard, thank you so much for being with us today. Please, the screen is yours.
Thank you, Marina. And welcome also from my side. I'm excited to be part of this webinar about the interaction of light with tiny molecules and what kind of effect this has on human health and the future of energy storage and energy demand. We will have three experts. We will have Professor Michael Hollig, who will be introducing us to the secrets of vitamin D. Then Dr. Sabine Kling will introduce a medical application that is important for the human eye, how daylight can help there. And in the end, Professor Greta Patsky will talk about artificial photosynthesis. As announced, there will be, we can answer one question or maximum two after each talk, but there will be a longer Q&A session after the third talk. So it's important that you use this Q&A function to enter your questions, please. And at the end, we'll have this quiz, so please keep your eyes and ears open. Maybe you will win the prize, which is the book Enlighten Your Clock, about how your body tells time. So, but now first we have a question to you, and we will do a little check-in, and we would like to know what is your disciplinary background. So we have a choice of answers. You might come from biology, medicine, vision sciences, chemistry, ecology, physics, architecture, and maybe you have another background which is interesting. So then please enter that into the chat. We are curious who is here. We have already an answer. Anthropology, David Harrison, welcome. Okay, so interesting to see that we have a great number of biologists, architects, physics, engineers. There's a person from vision sciences and lighting design, engineering. Wonderful. So now, now that we know each other a little bit, it's a big pleasure to introduce our first speaker, Professor Michael Hollig. He is a professor of medicine, physiology, and biophysics, and he's the director of several research units, the General Clinical Research Unit, the Bone Healthcare Clinic, the Heliotherapy and Light and Skin Research Center at Boston University Medical Center. He earned his PhD in biochemistry and did also a medical degree, worked as a postdoc at the University of Wisconsin-Madison, and then also in medicine at the Massachusetts General Hospital in Boston. He was the first to identify the major circulating form of vitamin D in human blood, and then he isolated and identified the active form of vitamin D. So he's a specialist of vitamin D who also analyzed mechanisms of vitamin D synthesis in the skin and various external effects, such as daylight, that are important for this vital process that happens in our skin. Michael, the floor is yours. We are looking forward to your presentation.
Well, hello, and it's a great pleasure to be here and to share with you my perspective on the importance of sunlight and daylight for your health. So I am going to give you a broad perspective in the few minutes that I have. People worry about conflict of interest, so I do consult for Ontometrics, Biogena, Carbon Amicus, as well as Soleus. And if you're interested, you can go to this website, either drhollig.com or edsresearchproject.org, where you'll learn a lot more information and many more presentations by me about vitamin D and the biologic effects of sunlight. Now, you may be wondering about this, which is, am I really an idiot to be talking about sunlight and vitamin D, because sunlight is bad for your skin? And there's no question that there's a lot of pros as well as a lot of cons for exposure to sunlight. And indeed, it was Akhenaten back in 1351 BC who appreciated the beneficial effects of sunlight for your health. It was Hippocrates who had prescribed heliotherapy and sunbathing, and Philostratus who claimed that Olympian athletes took sunbaths in order to strengthen their muscles and bones. But in the 1600s, these children in these alleyways in Glasgow, Scotland, not exposed to any sunlight, had developed classic rickets. By 1889 in Boston, 80% of infants had this unfortunate disease, causing severe growth retardation and these skeletal abnormalities. It was Sneadecki, a Polish physician in 1822, who realized that children living in the inner city in Warsaw had a high incidence of rickets, and those living outside of Warsaw did not, and realized that their sunlight was a cure for rickets. Now, who's going to believe a Polish physician in 1822? It would take 100 more years before Hessen Unger took children, put them on a roof of New York City hospital, and cured rickets. Sunlight, as you know, exudes energy. So how do you make vitamin D? So when you're exposed to sunlight, it's the precursor of cholesterol in your skin, absorbs ultraviolet radiation, converting it not to vitamin D, but to pre-vitamin D, which then by body heat converts it to vitamin D. I'm always asked this question: if you take vitamin D as a supplement versus getting exposed to sunlight, is there any difference? It turns out when you make it in your skin, it lasts 2 to 3 times longer in your body than comparing it to taking it as a supplement or from your diet. So how much? You never want to burn, can't look like this. And coming from New England, you never want to look like this. So we did a study and we asked the question: if you're exposed to 1 minimal erythemal dose, a light pinkness to your skin 24 hours later, how much vitamin D are you making? And it's about 15,000 to 20,000 units. So you can understand that your skin has a huge capacity to make vitamin D. When you look at the whole solar spectrum of light, daylight coming in, it's this tiny amount right here called UVB radiation that's responsible for the production of vitamin D in your skin. It's responsible for the evolution of vertebrates on this planet for over hundreds of millions of years, 290 to 350 nanometer radiation. So what about vitamin D and COVID? We're hearing a lot about this. Well, if you go back into history, Florence Nightingale in 1850 was opening up the windows and exposing the patients to sunlight, because sunlight exposure, she said, was really important for promoting health. And she said direct sunlight, not only daylight, is necessary for speedy recovery. Back when the Spanish flu hit in 1918, Spanish flu patients at Camp Brooks here in Massachusetts in an open air hospital realized that if you were exposed to sunlight when available, doctors noted severely ill patients improved more than those indoors, citing the combination of fresh air and sunlight. So COVID, of course, has devastated the entire world's population. And so we did a study and asked a simple question back in 2020, and that is, if you're vitamin D deficient, are you at higher risk for developing COVID? So we looked at 191,000 patient samples with Quest Diagnostics and showed that if you're vitamin D sufficient, you have a 54% less likelihood of acquiring COVID, and definition of 25-hydroxy vitamin D of 34 nanograms per ml. And look at this, you continue to improve that resistance even out to 60 nanograms per ml. We also asked another question: if you go into the hospital with COVID, right, are you more likely to die if you're vitamin D deficient? And sure enough, working with Dr. Magabouli in Iran, we showed that those over the age of 40, if they were vitamin D deficient when they walked into the hospital, they had a 51.5% increased risk of dying, right? We now know that essentially every cell in your body has a vitamin D receptor, and we're beginning to realize that neuropsychiatric disorders, infections, autoimmune diseases, and osteomalacia are all associated. Again, you can go to this website for more information. This is a picture I took when I took my daughter on safari. This is a Maasai herder. Their blood levels are 40 to 50 nanograms per ml. You would need to take 4,000 to 5,000 units of vitamin D a day to achieve that level. Now we know that sunlight, bright blue light, right, is important for controlling your biologic clock. But why is it that people feel better when they're exposed to sunlight? Can human skin cells produce a happy substance when you're exposed to sunlight, i.e. beta endorphin, right, causes the runner's high? So we did a study and we showed that it was UVB, not UVA, but UVB radiation responsible for producing beta endorphin in your skin. You can make beta endorphin in your skin. Beta endorphin is important for pain relief, feeling of well-being, relaxation. And look at this, 33 times more analgesic than morphine, right? What about autoimmune disorders? If you live at higher latitudes, you have a 50 to 60-fold higher risk of developing multiple sclerosis. If you live above Atlanta, Georgia for the first 10 years of your life, you have a 50% higher chance of developing MS. And the same thing for type 1 diabetes. Higher the latitude, higher is your risk. Cardiovascular disease. Vitamin D plays a critical role in the production of nitric oxide, right? Indeed, we also know that sunlight hitting your skin produces nitric oxide, which causes vasodilation and has a lot of other biologic effects. And guess what? Your hemoglobin, when hit with ultraviolet radiation, releases carbon monoxide, which is very important for regulating vasodilation, neurotransmission, relaxation, and antioxidant activity. So when you're thinking about sunlight, daylight, don't only think about making vitamin D, but immunomodulation, and as well as regulating even wound healing. World Health Organization recognized sun rays are warmth and light enhance general feeling of well-being, right? And stimulates blood circulation, production of nitric oxide. Some UV is essential to the body as it stimulates the production of vitamin D. There is no doubt a little sunlight is good for you, right? So again, looking at sunlight hitting your skin, it has a lot of biologic functions. Indeed, sunbathing could cut your risk of cancer, right? 1941, it was realized. If you live northern United States, you're more likely to die of cancer. And so now Dr. Lindquist, here now, more than 80 years later, shows very nicely all-cause mortality. Those that avoid sunlight, their survival, compared to those with most sun exposure. And death, avoiding sun, you're more likely to die than you are of being exposed to sunlight. And it's all due to avoiding death by having less cardiovascular disease, less cancer, and other conditions. And so I wonder. Here comes the sun.
So thank you very much. This was fascinating. So we have a question by Ali Heshmati. Does color of the skin has anything to do with the production of vitamin D? Are fair-skinned people different than dark-skinned people?
It's a wonderful question. We know, even in the United States, but worldwide, those with more skin pigmentation are more prone to vitamin D deficiency. Why? Because if you put on a sunscreen with an SPF of 30 properly, it reduces the amount of ultraviolet radiation getting into your skin by 97.5%. Typically, a person with skin type 5, very dark skin, more than 90% of that ultraviolet radiation is being absorbed to protect you, but it reduces your ability to make vitamin D in your skin by about 90%. So yes, people of color are more prone to vitamin D deficiency because they're less efficient in making vitamin D.
Okay. Another question was this mechanism of transforming the pre-vitamin D by the skin temperature, by temperature alone. Is there a way to explain this in a simple term?
Yes. So, you always think about enzymes being enzymatic, right? Accelerating a process in your body. We observed that Mother Nature cleverly designed a system. So when you're exposed to sunlight, instead of taking several hours to days for that pre-vitamin D to convert to vitamin D, because it's in the plasma membrane in a certain position, it automatically induces it to immediately convert to vitamin D, which then changes its structure and gets ejected out of the skin. So instead of taking hours to days to convert, this non-enzymatic membrane-enhanced activity will cause you to make vitamin D in your skin within a few hours.
There is an interesting question about the optimal exposure to sunlight. You said you need a little sunlight, but what is a little? And there are advices to avoid sunlight because it causes cancer.
Exactly. So time of day, season, latitude, degree of skin pigmentation. Just to give you an idea, if you live at the equator, and you go out in the morning at 8 o'clock in the morning, you will make no vitamin D. You only make vitamin D from about 9 to 10 is when you really begin to make vitamin D, and it abruptly ends at about 3 p.m., even at the equator. In the wintertime, you make no vitamin D if you live above Atlanta, Georgia, from about November until March. And so how do you know how much vitamin D, how much sunlight? There's only one thing to do, and you can see on the slide, dminder.info. It's an app that we developed that's free on your Android and on your iPhone. It'll tell you anywhere on this planet how much sun exposure you can have to make an adequate amount of vitamin D, and then it warns you to get out of the sun so you do not get a sunburn. This concept of being out there for 10 or 15 minutes, which is what the press usually promotes, and even the World Health Organization, makes no sense. Because if you are a very light-skinned person at the equator at noontime, 15 minutes will burn you, right? But if you have very dark skin, you won't make enough vitamin D. So you have to take all of this into account, and this app will help you do that.
Cool. What about sunscreen? Are we shooting ourselves in the foot if we put on sunscreen?
And so my recommendation, and also on the app, is that you can go out for a very short period of time, right, to take advantage of the beneficial effect of the sun, and then to put on the sunscreen. SPF of at least 30, preferably 50, because most people don't put it on properly, so that you have good sun protection. Also, when I recommend to go out into the sun, always protect your face and your upper hands, because they're the most sun exposed and most sun damaged. But arms and legs, abdomen and back are perfectly fine.
You mentioned the health conditions of children who were kept in the dark, so to speak. Is there a recommendation how schools should look like to improve exposure of children to sunlight or daylight?
It's a good question. I mean, at least when I was growing up as a kid, we always had a recess before lunch, and we were always outside for about 10 to 15 minutes, outside playing in the sun, right? And then for lunch, we often, after lunch, we would go outside again for 5 or 10 or 15 minutes. And so, and then as a child, I was outside all the time after school, right? Playing baseball and the like. We don't do this anymore. We're always inside. The kids are always on computers. Parents are worried about no sun exposure at all. In my opinion, I think that that's the wrong message. Just like anything else in life, sensible sun exposure is good for you. It's healthy for you. I showed you, you make beta endorphin, you make a whole host of chemicals in your skin, all to promote good health.
Wonderful. This is a whole new world of interacting with the sun in a sensible way. Thank you so much, Michael. And maybe we then move to the next talk. We will stay in the medical field. So Dr. Sabine Kling is a research scientist who holds an MSc and a PhD in visual sciences from the University of Valladolid in Spain. She did also an engineering degree in physical engineering at the University of Essen in Germany. And she focuses her research on optical imaging and photochemical treatments in the area of ophthalmology. This is the science of medical treatments of the human eye. So we are looking forward to your input. Sabine, welcome, and you can share your screen.
Yeah, thank you. So I'm happy to give you an insight into photochemical treatments in ophthalmology today. And treatment with light is particularly interesting in the field of ophthalmology because it does not require any contact and therefore is desired for ophthalmology because the eye is a very sensitive organ. And so there are two conditions that are particularly interesting for the treatment of photochemical treatment. The one condition is keratoconus, and here you can see we observe a focal localized outbulging of the corneal tissue, which is because the tissue weakens in that area and therefore substantially bulks out and deteriorates vision. And it is unfortunate, however, that this disease is progressive, and therefore there's nothing typically that can halt it. And so the standard way of treating such a condition is a corneal transplantation, which is not desired in young people where this condition particularly often is observed, because the transplantation has a lifetime of approximately 15 years, and therefore this is not an ideal solution. And another issue with this keratoconus disease is that there is poor contact lens fitting, and so these people really suffer from visual defects, so they cannot see well. And another condition that is interesting for photochemical treatment is infections keratitis. There we also have a localized lesion in the tissue, and this is typically infected either with bacteria or with fungi. And an issue with that condition is that also it can progress if it's not quickly treated. But the problem here is that it is often not sure which microbial, whether bacteria or fungi are causing this disease, and therefore the treatment would be different depending if one or the other is the cause. And doing a swab and sending it to the lab for analysis, this typically takes a few days, and this is already too long to wait with treatment. And in these both conditions, photochemical treatment is particularly interesting because for keratoconus, it can induce tissue stiffening. So it can create new crosslinks between both collagen fibrils and the extracellular matrix components. And with respect to infectious keratitis, the photochemical processes induce microbial killing. And this is sensitive to both bacteria and fungi. And also importantly, there is no known mechanism how antibiotic or how resistance could develop. And therefore, this is so far considered a very promising treatment. Now let's see how photochemical treatment works and what it is based on. This is just to show you how the eye would look after treatment. So you can see there's a substantial improvement, and it will further heal on. And so photochemical treatment is based on a photosensitizer and the irradiation with light. And the photosensitizer is basically a chromophore. And this is a molecule that has an energy difference between two molecular orbitals that falls within the visible range of the spectrum. And this means if light hits that chromophore, it can get absorbed and excite the electron from its ground state into an excited state. And this is a day-to-day phenomenon that we also observe in other areas. Once the molecule is excited, different mechanisms can occur. One that is everybody probably familiar with is fluorescence. So the photon just gets excited and then falls back into the ground state. This is a very fast process, and it results in fluorescence. Now, there is another possibility that from the excited state, there occurs a mechanism which is intersystem crossing, and then it transfers to an excited triplet state. And this state is longer lived. So we are talking about the range of milliseconds. And therefore, it is more rare, but also as it remains longer in that state, it has more potential to react. So one mechanism that can happen here as well is phosphorescence. You probably know there's a delay between the irradiation and the time when the molecule begins to phosphorescence, sorry. And this is, you probably are familiar with such lightning in the dark pieces. And another thing that can happen from this triplet state, this is the type 1 and type 2 photochemical reaction, which is the photochemical mechanisms we are interested in mainly in the ophthalmic application. You can see here on the right, an eye is being treated, and it actually shows also fluorescence, which occurs simultaneously, but this is not the actual mechanism that we want to see. However, type 1 and type 2 mechanisms that occur at the same time They are they are dependent on oxygen, and they create reactive oxygen species, either by type 1, which reacts with the substrate and the chromophore and causes typically hydrogen peroxide, or by the interaction with molecular oxygen and the creation of singlet oxygen. And so it is, we have previously investigated the effect of oxygen onto the efficacy of photochemical treatments in ophthalmology, and we could show there is a strong dependency. It is much more stronger in terms of stiffening the tissue than killing the bacteria or fungi. And therefore, most recent approaches aim at administering oxygen during the treatment. Now, in terms of light irradiation, this depends very much on the absorption spectrum of the photosensitizer. Now, in ophthalmology, we use typically riboflavin as a sensitizer, which is vitamin B2, and it has, as you can see, 4 absorption peaks. And now for the clinical treatment, typically people select 1 wavelength, and this is used for irradiation. In this particular case, the first 2 peaks would be desired because they have very high energy and would be best in terms of efficiency. However, they also get strongly absorbed from DNA and have the potential to damage DNA. And therefore, these 2 peaks are not selected. Then the next, the third highest peak in terms of wavelength energy is in this at 365, and this is the actual one used for the treatment. It has a moderate UV energy, a moderate penetration depth, and it is not absorbed from DNA. And the other, the 4th peak, this is actually just, it has lower intensity, but still could be used, but normally it's not done. Now, light is also provided from the sun, as we know, and if we look at the emission spectrum from the sun and what reaches on the Earth's surface, we see there is very little proportion in the UV, in high UV range, which we did not select in the riboflavin absorption peaks because they are potentially damaging. And so riboflavin could be excited also by sunlight. And this is a very exciting technique because sunlight is everywhere accessible, and also it comes at no cost. And so there have been attempts to study whether photochemical cross-linking in ophthalmology could also be performed using the sun. And as you can see in this graph here, riboflavin plus sunlight actually induced the strongest stiffening effect in this study here. Of course, you need to take into account that the irradiation time was overall longer than for the 365 or 436 nanometer irradiation only. But still, this is very interesting, as we can see that sunlight has the potential to take over the role of irradiation. Now, one issue that occurs with sunlight is that we have a lot of intensity that is provided from the sun, which is not used. And so we need to also consider what is the safety of this treatment. But first, let's have a look at how we could bring this photochemical treatment further out of the eye clinic, because also, as I mentioned, vitamin B2 is used as a photosensitizer, and this also can be taken up by dietary. And we showed in an earlier study that the levels that can be reached in corneal tissue when administering the riboflavin orally, this is approximately 1,000 times less, but still it has been shown in a very recent study that's in a prospective study in humans actually, that oral administration of riboflavin for 6 months and a natural daylight exposure for 15 minutes a day could stabilize the condition of the keratoconus. And most importantly, no adverse effects have been observed. And of course, this is a small study that needs further confirmation, but it is at this moment very exciting news that sunlight and dietary riboflavin uptake can actually treat a condition in ophthalmology. And now with respect to treatment safety, typically the photosensitizer determines how much light reaches the posterior parts of the eye. And so the higher the photosensitizer concentration is, and the less light reaches the eye and potentially damages the posterior layers. Now, this is a bit of a problem because, as I said, the riboflavin concentration that we can get orally is much less than it can be achieved in the medical environment when administering it directly onto the tissue. And therefore, it is important to make patients clear that they should not watch directly into the sunlight, but rather just behave naturally, as natural sunlight typically is not an issue if the intensity is not too high. So it is rather moderate levels that can be used of sunlight for this type of treatment. And this is just to mention safety again. So what happens is light can enter into the eye as it is necessary, as we want to see that. And it depends on which wavelength actually is administered. And the sunlight, if too high intensity levels of sunlight hit the retina, it actually also induces photochemical reactions that finally damage the tissue. This is because there are endogenous chromophores already available in the retinal tissue. This includes the flavoproteins, hemiproteins, melanosomes, and lipofuscin, among others, that also absorb light. And if the intensity is exceeded, then they induce this photochemical mechanism, which finally results in the destruction of the tissue. And I want to show you, just to conclude my talk, an example of what happens actually if you look directly into the sun. This is a patient that watched the solar eclipse without any protective goggles. And you can see on the macular, that's exactly the same shape of the sun that has been damaged with a photochemical damage. And so in conclusion, photochemical treatment is able to prevent corneal transplantation in keratoconus, and it can kill a broad range of microbes in infectious keratitis. But using sunlight for irradiation will bring this treatment option even into remote and poor areas. But at the same time, it requires adequate training in order to prevent retinal photochemical damage. Thank you.
Thank you very much, Sabine. Fascinating. So with regard to your last statements, what would then be enough, or how can you make sure that you get the right dose of sunlight?
So yeah, for now, I mean, we know that if you just go out on a daily basis, this typically does not harm the eye unless we are in an extreme environment, such as close to the sea or on the snow. And so just using the common daylight exposures that is currently considered safe. And according to this one study that has been performed, 6 months have been shown to be sufficient with a daily exposure of 15 minutes. So starting from that study, we could possibly evaluate whether a shorter period of time is already sufficient or not, and then accordingly calculate the timing that is really needed for sunlight exposure.
Great. And another question relates to the dietary intake of sensitizers and your medical intake. So do we have an adequate dose already by eating normal food, or do you really need an additional boost of sensitizers?
Yeah, this is a very good question, but this has not been investigated yet. So, I mean, it's also difficult to extract the tissue from a human patient and just to determine how much riboflavin is inside there. So I think this all needs much more studies to be done in order to get some conclusions on this question.
Yeah, interesting. I also, maybe, are there other applications? I mean, you are working in the field of ophthalmology, but there are also diseases of the skin, and one maybe could burn away some bacteria. I don't know. Are there applications to cure skin problems?
I haven't. I mean, it's photochemical treatments are used to treat skin cancer, for example, to get rid of the cancerous cells. But one issue, I mean, it could of course also be applied to disinfect a wound. But what I think is the main difference to ophthalmology is that in skin we are less limited with the intensity that we can administer, and therefore much higher or more aggressive agents also could be used to fulfill the same effect. So we are less limited in dermatology.
Yeah, there's a question coming in about the best time of the day. So you related to maybe a moderate sun exposure. What would be the best time of the day to get the right dose?
Yeah, that's difficult to answer. As we also saw from the previous talk, this depends very much on the latitude and on the period of the year where we are in. So I don't know exactly. Sorry, I can't answer this question. I think in total the whole intensity. I mean, this was at a moderate latitude, the study that has been conducted, and so it's not. I would say it's not excessive, the irrigation that is needed.
Yeah. So it's probably better in the morning hours or later, not exactly at midnight.
Yeah, in the afternoon probably, right?
Okay. Yeah, thank you so much again. This is really interesting. We will have a chance to discuss more later. I think now it's time for Marina to share her visual harvesting. Please, Marina.
We're not hearing you, Marina.
Can you hear me now? Thank
Yes.
you, Bernhard. Give me just a sec to prepare. Super quick. Here we go. Let me share my screen. Might take a little sec. Can you see my screen?
Yes.
Yes.
Okay, so we continue our journey today on the last part of our trip, coming from the sun to the cells. We spent some time with Professor Michael Holick. He's been talking about vitamin D, effects of COVID, effects on why do we feel good when we're exposed to sunshine, endorphins, vitamin D. Then we had this amazing talk with Sabine Kling. Talking about keratoconus and infection keratitis, and the research related with sunlight exposure and riboflavin orally uptaken. And lastly, talking that this treatment could bring the treatment to poor and remote areas, but only if we have proper training on how to apply this photochemical treatment. I hope this helps. Thank you so much.
Wonderful, Marina. Great. Yeah, I like the idea that sunlight makes us happy, and that there is not only vision, but also a vision how to apply these things. Wonderful.
Absolutely.
So we come to the third speaker of today. Professor Greta Patsky got her PhD from the University of Hanover, and Venia Legendi from ETH Zurich. She moved to the University of Zurich, and she's a food professor since 2016. Greta Patsky focuses her research on the synthesis and monitoring of nanomaterials for environmental applications. And her group has a special interest in understanding mechanistic pathways and also to apply these materials to chemical energy conversion. So she is heading a research priority program at the University of Zurich, and there her team is studying a wide range of molecular and nanostructured catalysts for artificial photosynthesis. So we are really curious what you're up to, and thank you for joining us, Greta.
Well, thank you very much for that very kind introduction, and thank you so much for inviting me to this symposium. I'm really honored to participate today, and I hope you can hear me quite nicely and see my presentation now. And
your presentation is not up yet.
Oh, I've shared the screen, actually. Can you see it now?
Wonderful.
Okay, thank you. Thanks for alerting me. So I will be very happy to introduce the concept of artificial photosynthesis today and to speak about what basically sunlight can do for us in terms of covering our future needs for commodities and clean fuels. And so to this end, I wish to say that the solar energy is basically our inexhaustible energy resource. As you can see from the left-hand side of the graphic, it outperforms all the other energy sources, sustainable or not, that we do have available. So if we tap into this, we can basically safely cover our future fuels and chemicals and all the things we need in daily life. Not only from sunlight, of course, but we also need other inexhaustible ingredients, and that could be carbon dioxide, water, and nitrogen. That sounds like a dream to convert these resources into the stuff that we use in our civilizations. But to that end, we need to make chemical reactions work, and they don't go on their own. They need the concept called catalysis. And now nature and natural photosynthesis is the master for us, from whom we learn how to convert these resources into complex carbohydrates, for example. And in chemistry, we are learning now how to work with the solar light and make the right catalysts. And today, I'm going to show you how that works so that you can take home a little bit from that. So in nature, as we all know, carbon dioxide indeed and water are converted into sugars, roughly spoken, and dioxygen with the help of sunlight. Underneath, though, is a very simple skeleton process. That's this splitting of water with sunlight. That comes first to make the hydrogen that actually reduces CO2. And in this process, which is not trivial to make work with sunlight chemically only, we have the fact that we have to produce dioxygen. And this is not easy. O2 minus in the water does not want to give up the electrons. It just wants to keep them. And so we need a lot of energy and a good catalyst, basically, to rip off the 4 electrons and use them to reduce our protons and also make H2. So this is the playing field for catalysis in this case. And how does nature do it? And first we need to talk about, of course, get all on the same page, what a catalyst really does. It is not a magic powder. It's also not a mystery. It simply is a helper who makes the job more doable. Like we chop down our tasks in daily life, a catalyst chops down the usually very high energy barrier for demanding reactions. And so in here you have a high energy barrier that needs to be overcome to make the reaction go. And the catalyst interferes and chops it down into doable tasks. And those can also make the reaction proceed faster. And ideally, the catalyst comes out unchanged, ready to enter a new cycle of reactions. And nature, as I said, is a master in doing natural catalysis, and we need to make that work. Like in that cartoon in here, that we have catalyst that makes the solar light split water for us. And this we call the water splitting catalysts. And as the water oxidation, the oxygen making is actually the harder part, we also speak about water oxidation catalysts in here. And so nature's water oxidation catalyst is actually a a little wonder. Basically, it is a very small inorganic catalyst having only 4 active manganese centers that form some sort of cube that also has a calcium atom that is much debated why nature uses it actually. And this is in a protein with, say, 50,000 shielding organic atoms. So this protects and assists this very little catalyst in making the oxygen evolution work. And since chemists discovered this motive, they have been extremely intrigued and trying to copy it in various ways, ideally to split water in a very simple and low-cost way. But this journey is still going on. I prefer to show some examples from our lab to make sure that I know what I'm talking about. And for example, in our lab, as in many other labs in the world, we have copied out a cuboidal catalyst that indeed oxidize water, but we also learned how this works, but also how not to copy from nature. So this is really a very difficult approach to do it exactly like nature does, the water splitting. So therefore, in technology, you have different approaches. I want to show them to you today to see where we stand and what we can do already, and how close the goal is to make green hydrogen with sunlight in different ways. So the softest and most nature-inspired way would surely be the photocatalytic way. But here we have some sort of traffic lights, red lights, yellow lights, and already the technological green light. And in professional terms, we call this the technology readiness level of an approach. So the nature-inspired approach, photocatalysis with 2 different catalysts like in nature that take care of making oxygen and hydrogen, is indeed very intriguing. A magic powder working with sunlight and hydrogen, oxygen bubbling out, very simple. However, the chemists like us need to do a lot of work still to increase the solar to hydrogen efficiency. This is the, roughly spoken, the conversion efficiency of solar light that actually winds up making hydrogen. That's too low. But that's, as we shall see, one of the few remaining problems. We fare better in the photoelectrochemistry, where we put the catalyst more technologically approachable on an electrode, in this case photoanode, and let the sunlight shine on that one, and the catalyst is more safely embedded in here. And then we can also have separate processes for hydrogen and oxygen making. This is already on a good way, yellow light, so to speak, and the green light is already given for outsourcing the solar work. So there we use photovoltaics basically to harvest the solar light. That's all well known. We all know this on our rooftops and elsewhere. And then we can use this green electricity to drive a simple electrolyzer that we all know also from our education. This takes care of the water splitting, but driven with energy that comes from the sun. However, we also need to sort out some catalytic tasks in here, but the technology is ready to use. We will also have some facts on this a couple of slides later. So let's see where we stand in research. I think that for the chemists, the most intriguing version is still to do it like nature does, pouring a powder into water and simply harvesting softly and everywhere on the go the hydrogen. And as I said, some people were saying, oh, that's not possible and it's too risky. But in fact, in 2021, the group around Professor Doman and colleagues had a breakthrough pilot project where they really did 100 square meters of such a field experiment with the homemade catalysts. And all the concerns like this can explode or the gases cannot be separated, they were nicely worked out in this experiment. And the punchline was they even had the reactor burned down intentionally and no super explosion happened, but the damage was, let's say, less worse than they had expected. So this is the way to go. But as we said, in the chemical labs, we have to get the efficiency of these catalysts up. Well, in our lab, we also heavily work on this task, and we had some good news last year. Actually, a little bit like in nature, where the photosystem actually falls apart and reorganizes itself from time to time. We have to basically leave catalysts alone sometimes so that they do a good job for us. And in this case, we found out that if we have simple cobalt salts that are irradiated with visible light, they do the job on their own and self-organize into better catalysts than we could ever make with a molecular synthesis. And then let's see what the matter is in the electrochemical way with the electrodes. So we have selected one of the many excellent studies in the field, and this device is like a little block, a monolithic block that can be immersed into water and exposed to sunlight. And then when using the right catalysts in here, still noble metals though, that are very costly, it is possible to come much higher in the solar conversion efficiency. So almost close to the theoretical limits and almost 20%. That's a different sort. And now we can play with the semiconductor and the coatings and the robustness of the device. And then we would have our dip-in device to make hydrogen for all of us very cleanly, ideally. On the lab research scale, this is, however, a different story to understand what's going on with the atoms on the surface. There we undertook, that's also shared with many other researchers in the field who work along these lines, but in our lab we undertook a study where we managed to track the oxygen atoms with light again, how they hop around on the real surface of this electrode, and we found out how fast or slow they move, what species they form, and how we can persuade them to make the oxygen formation please a little faster. And this is very far how we can go with relatively simple experiments to understand how these materials work and how we can bring them towards application. And the punchline in here is it's iron oxide, almost simple rust, a very ubiquitous and cheap material. That would be a future great candidate. Okay, and last but not least, the water electrolysis plus photovoltaics is proceeding fast. Here we only have to sort out basically the price issues on the market, but the companies and many solar farms are ready to work with more than 10 megawatt electrolyzers and really get that project going, make cheap green hydrogen that's cheaper ideally than fossil fuels. And also in our lab, we stick with our cobalt and iron compounds. And in order to make the catalysts a little better, we need again to understand how they work. We had the nice example that we could use the same catalyst on both electrodes to produce both hydrogen and oxygen. And we went to a so-called synchrotron facility to watch the catalyst at work, how it really operates on the atomistic level while it generates water. This was fascinating, watching it work and learning how we can improve these systems. On the last slide, I want to show you where the journey is going and what the visions are for the future. So in photocatalysis with simple powders, researchers have also proposed just to take care, for example, of the oxygen evolution with a magic powder catalyst and outsource the more convenient proton reduction in the second process, and then we can still pour the powder, connect the electron flow to hydrogen making and have it in a very low-tech way. Very fascinating. In photoelectrochemical, the trend goes towards replacing the oxygen formation altogether by tapping into biomass. Biomass holds a lot of promise because it has so many great chemical compounds that we need, but how to untangle them? It's a little bit of a mess. And so when we have the right electrodes, we can basically peel out vanillin or other commodities that we really need, also with the help of photoelectrochemistry. And lastly, the question of electrolysis and photovoltaics is more or less an economic question. We need to get the price down, the capital expenditures for electrolyzers need to be lower, the lifetime needs to be longer. It's pretty much technical stuff that's in the pipeline now, but surely we will see that in the next 10 years or earlier. Okay, that's my opinion on the artificial photosynthesis that would hopefully help to make a world greener and cleaner. And lastly, I also wish to thank very warmly my group for all the beautiful results and the hard work. I wish to thank the University of Zurich for our aforementioned special research program, LightCheck, all the colleagues therein, and also the Swiss National Science Foundation, who supports very much this research. And all of you for having me and your kind attention. Thanks a lot.
Thank you so much, Greta, for this wonderful overview of the different, 3 different ways to make green hydrogen. So we have some questions. Hubert Klampner wanted to ask whether this solar hydrogen is really competitive for the large energy transition that's ahead of us. I think it relates to what you said in the end, the PV to electrolysis method. When will that be competitive? You even mentioned that it could be cheaper than fossil fuels, which might be it would be wonderful, but how long does it take?
Well, that's a question, frankly, that I feel not competent to answer on my own as a scientist. I think I rely here on external sources that say, indeed, that it is possible to reach that goal, but it all depends on several factors. It depends on how long we go on using fossil fuels, especially at the moment. It's a very tricky question to answer, but it is in principle, it is possible. There are various studies out that if you have enough access to solar energy in solar-rich countries, that this can be done. It also depends where this is performed. If you can harvest solar light in abundant ways, that's surely the place to go. If you have solar deprived regions, probably there you should not engage in this hydrogen production. And surely we will also need other approaches. This will not only be the only solution to the future energy needs, but certainly one of them.
Yeah, you mentioned the risk profile, and Michael Walczak asked whether it's not too dangerous to implement such technologies in cities or urban areas. Would you go outside, somewhere into the desert with that?
Yes, definitely, absolutely. So I would say the experiment by the Dolan group showed very nicely that basically the damage will be there. And so it's out of the question that this needs to be done in an open field and away from urban environments. If we go for the natural water splitting. I'm sorry, an electrolyzer, of course, can be operated everywhere in a clean facility. That's a different story. But the visionary stuff should be done in open fields, and ideally you have it closer, that you have a solar farm in nearby, let's say the hydrogen evolution facility. And then, of course, it's always the food versus fuel conflict, how much land you want to sacrifice for that. But I think if you do photovoltaics anyways, that will be the most space-consuming affair. The electrolyzer isn't so large in the very end, if you go for the third technological option.
Okay, yeah. You also mentioned the potential of biology, and Burhan asked the question whether you could couple it to CO2 reduction in a way to mimic real photosynthesis.
Absolutely. This I forgot to say. Thank you for this excellent question that gives me an opportunity to apologize that I was totally zooming in on water splitting. Of course, that's a huge research community dealing with the CO2 reduction chemically. This is now the opportunity to honor this work. There's a huge community working directly on that point, really converting CO2 into other valuables like the plants do. But the problem in here is that you can have many products from the CO2 reduction. The so-called selectivity is a bit of an issue. So often you have a mix of products when you choose the wrong catalyst, and these are difficult to separate. But absolutely, all right, this is underway. It really is. But I would, for details, kindly refer to the colleagues in the community here.
Okay, okay. Yeah, I have a question from my side. I mean, you nicely showed these three different pathways, and you said the first one has this efficiency problem, but the second is close to the theoretical limit already. What about then the combination of PV and electrolysis? How does that compare in terms of efficiency? How much do you lose?
Oh, actually, I don't have this precise number from the top of my head, but of course, there are always different numbers. The overall efficiency, it always depends on what kind of electrolyzer you use. There are different types and so on, but I wouldn't nail myself down on a percent level, but it is for sure the heart of the question is absolutely right. You lose energy when you have a two-step process. And in fact, if you just have two steps, you have the efficiency of each step multiplied by each other, and that's the overall efficiency. So you can basically take the typical efficiency of solar and the efficiency of electrolyzer, multiply that, and then you will plummet with the overall efficiency. That's clear. However, the calculations say it's still good enough to make competitive prices if you have cheap technology and quick access to solar energy. But the question gives the reason why we still work on the other ways, because they are direct processes. If you use the solar light directly with direct catalysis, you skip that coupling step and have the overall efficiency plus less technology. And this is why we still work on this research very intensely.
So there's another question related to risk profiles. And as a chemist, I mean, we are all aware hydrogen is, well, you have to handle it with care. So is this really just an industrial product that is used under high safety measures? Or could it be in the end also part of the consumer world?
This is a great question. It pertains to the future hydrogen economy. There's a big debate going on whether we should all use hydrogen itself on a larger scale. That's the debate, basically fuel cell cars versus electric cars. So of course, at the moment, it seems like the favor is on the side of battery-driven vehicles. But fuel, for example, fuel trucks, hydrogen trucks are also used in Switzerland. There are certain companies and an active network that carries goods all over Switzerland with hydrogen fuel trucks. So that's definitely an option. As I said, it will not be a total hydrogen society, but this we can use safely, and it is used safely already to bring goods to the retailers or so. On the other hand, I'm an advocate of using hydrogen further. It's basically, as an energy carrier itself, to burn it off is also a so-so thing, but it's great for making further chemicals. The first step would be making methanol, which is a liquid fuel. And then we could use that liquid fuel much better with the infrastructure that we currently have. So it will always be a mixed portfolio, certainly not an all hydrogen society, because we also need to get work done on the fuel cells. But certainly it is, if you handle it right, it's also relatively safe. But you have to pressurize it, you have to store it then in bottles and so on. And so if you can, convert it further and use those chemicals. And also, last but not least, we need ammonia as a fertilizer to prevent world hunger. And a lot of clean hydrogen could go into reaction with the nitrogen to cover the world's fertilizer and ammonia needs. But also, this is also current discussion.
Yeah, you are right. So thank you very much for your fascinating insights. And I think we are now moving to a more general session of Q&A, and I would ask Stephanie to help me pick questions, and maybe you already picked some questions. And the audience, if you still have questions for also the other two speakers, please put them into the Q&A. Thank you.
Yeah, thank you, Bernard. So the Q&A was also very busy, and there was one question answered in the chat, but I want to put it here again. It was to the first speaker, to Michael. Is there any relationship between sunlight exposure and sleep health?
Please ask the question again.
Is there any relationship between sunlight exposure and sleep health?
Yes, and so I had responded to that question. And the answer is that we know that about 40% of the adult population living in northern and real southern latitudes have what's called seasonal affective disorder. And that's caused by the decrease in intensity and duration of sunlight. And as a result, you can't suppress your melatonin levels. And melatonin, of course, makes you sleep. And so how does that relate? Well, it relates because as the sun is going down, right, that's giving you the signal to the brain to stimulate melatonin production to put you to sleep. But if you're now on your computer or on your phone, it has a lot of blue light. And it's the blue light that actually suppresses melatonin production. And so as a result, you could have a difficult time falling asleep. So if you really do follow the daylight cycle, where the daylight intensity and duration is beginning to decline, and you're not exposed to high intensity light, especially blue light coming from all of these electronic devices, it will definitely enhance your sleep.
Thank you. I just continue with another open question I still see in the Q&A. It is from Sandeep. How do LED lights help indoor plants for the photosynthesis as against the sunlight? I think that's for our last speaker.
Well, thank you for the great question. I have to say I'm not a plant biologist. I can answer the plant question on an empirical level. Actually, I treat my own plants with LED lights over winter, and they grow a lot. So the practical answer is yes, they do. And of course, we cannot simulate the entire solar spectrum with an LED lamp, but if you have, there are certain plant lamps with some sort of wavelight spectrum cutouts, and they seem to do a good job, basically. But of course, you can see the difference if sunlight comes up again in spring.
All right, thank you.
An opportunity also maybe to make greener agriculture and use it year round or so. I absolutely believe in these products.
Thank you. I also received another question for you through the chat, and that was, do you think that someday this process can be incorporated in human skin as unlimited free source of energy?
Ooh. I think with the human skin, we learned in the first talks that probably the human skin is already energizing us a lot, and that would turn us into plants and leaves technically. So I think our bodies are not so equipped for this. It would be, maybe evolution will help us a little, but at the moment I don't quite see this. But I think we should follow Professor Holig's advice and expose ourselves with caution to the sun to benefit already from the chemicals that we can synthesize with the sunlight. Yes.
Can you permit me to further that question?
Sure, go for it.
So this is the issue, okay? And this has been thought about by NASA 35 years ago, right? As we begin to explore other planets, right? Finding energy, growing plants and other sources on a spaceship is going to be difficult. And wouldn't it be interesting to actually incorporate chloroplast, right, into your skin so that it can generate a source of energy just by you being exposed to sunlight? And food sources are becoming incredibly limited on this planet, right? As the population is growing, would it make sense actually as a simple way of enhancing the availability of energy just by being exposed to sunlight?
Yeah, thank you for these questions and your answers. Bernard, do you have another question? Otherwise, I will go for another open question I see in the Q&A.
Yeah, go for it.
Okay, this question comes from Michael Heinrich. There are major challenges in implementing such systems. Could they be run around in the global north if such production system would be positioned, for example, in the Sahara? How would one ascertain that it gets to where it needs most?
Ooh, this is also a touchy question. As I said, if we say that if we use solar-rich regions for making the current and then electrolyze, it's always geopolitics involved. And so we have to act responsibly. Surely we have to rethink the distribution. I mean, the technical shipping of hydrogen, this is not such a big problem, but how to say, we have to make solid agreements, and we also have to look into totally different regions than we do now to cover our energy needs. And this is also, I'm not qualified as a chemist to say more about it, but I think it would also be opportunity to make new partners eventually globally. And in the global north, I think we cannot cover all our needs continuously on such a level with photovoltaics only. We need also further fuel sources. Yeah.
Thank you.
Thank you.
Bernard, do you have more questions?
I don't see many more. If the three speakers would share their vision, what is the most important step that will help people take advantage of the sunlight? Is it communication and knowledge, or is it behavioral change? The same would be true for Greta. What do you see? Do we know enough to now implement the hydrogen society, or can we do that only in 10 years? And to Sabine, what is the readiness level? Greta talked about the readiness level of the technology in hydrogen. What is the readiness level in ophthalmology? Maybe we start with Michael. What would be on your wish list? What would happen for vitamin D?
The good news is that the World Health Organization, right, no longer is considering exposure to sunlight to be only carcinogenic. They recognize the importance of feeling better and making vitamin D. I think that there needs to be better communication as related to environment, time of day, season, latitude, degree of skin pigmentation. And I think the app that we developed, which is free, can give you some insight, because what it's doing is it's taking the information from the satellites, how much UV is actually coming into planet Earth at any place on this planet. And we relate that to the skin type and to your age and everything else to give you a good insight as to how long you can be outside to get some sensible sun, to make some vitamin D, and then to put sunscreen on or sun protection to prevent the damaging effects. So bottom line, take advantage of the beneficial effect of sunlight and prevent the damaging effects due to excessive exposure.
Wonderful. So in 1 minute, Sabine, what do you think is the readiness level? Where will this lead us?
Yeah, well, I think at the moment this was a proof of concept, so it's at the very beginning, but at least this was promising, and I think much more research is necessary to define also the threshold, what is minimally necessary, and also where is the damaging threshold. So I think similar to sunlight and the skin, there will also be a threshold where it is beneficial and beyond where it will damage.
Okay.
So I think much more research is necessary in this regard.
Yeah, and Greta, would you also say you need more research, or should we do something about using hydrogen?
I would say we have to do something and do research in parallel, because the point is we cannot eat electricity. We need new chemicals and new commodities, and we need to feed the world. So we can start with what is ready, PV and electrolysis, and then we can always in parallel keep researching on the other methods, but we really have to take the basically first step and produce the stuff. I would say we are definitely ready to do so. And we, as I said, we cannot eat electrical current. We need new sources of fuels and chemicals that are really, really sustainable.
Wonderful. Let's use the momentum. But now we are coming to the quiz. So it's time to answer some questions. And who will bring up the quiz?
It will come in a few seconds, I think. June will share the slides.
Wonderful. So the quiz will come in questions, and you will have to. The first one is about, of course, the biochemicals that are not produced in the skin.
Sorry, Bernard, to interrupt you. Maybe just inform the people they have to take their phone and go to menti.com, and there they have to enter this code that they see in the screen in the top, and then they will see the questions there.
Thank you. So menti.com and then 23865148. 23, 86, 51, 48. And then you are ready to go, I think. So this is the question. What is not produced in the skin? So there's vitamin D, carbon dioxide, monoxide, etc. So time is running. You have to choose the one which is not produced. Okay. So the winner in this quiz is carbon dioxide, but we will see. Then comes the second question about ophthalmology. What does not induce the desired stiffening killing effect? So again, what is the fake news here? What does not induce the desired effect? Fluorescence, phosphofluorescence, type 1 reaction, type 2 reaction. Do you remember? Oh, there's a broad distribution, but the winner is the first one, fluorescence. Third question. So here we ask a question about the highest technology readiness level. Solar cells, biomass, iron oxide, water electrolysis, simple photocatalyst powders in solution. What has the highest technology readiness level? Oh, the winner is the yellow one, the D, yeah? Okay, we will see whether this is right. Now, the last question is about animals that have adapted astonishing ways to cope with too much sunlight. And which of the following statements is not true about zebrafish, kangaroos, foxes, deep sea fish? You remember? Or what would you choose? Okay, again, there is a clear loser and a winner, but you see what is correct. So we have some leaders here. There is somebody called Puffy with 2,484 points. So applause, applause. But Puffy, you have to send an email to office@Daylight Academy. Just please send an email to office@Daylight Academy, and then you will receive this wonderful prize, the comics book about daylight. Thanks for participating. And now I hand over for the closing words to Katharina. Katharina is Associate Professor at the Department of Molecular Biology at Umeå University in Sweden and the Speaker of the Daylight Academy Steering Committee. So Katharina, the floor is yours.
Thank you, Bernhard. I would like to say, now that we come to the close of this year's Daylight Awareness Week, we can really look back to 3 days of very thought-stimulating talks and discussions. We made stops at the journey of daylight from its origin in the sun all the way through space to Earth and into all cells or into cells of organisms and even the photovoltaics. So in the name of the steering committee of the Daylight Academy, I would like to express our thanks to all the speakers and all the people who contributed. For example, the speakers of day one was Dr. Alex Young, Professor Martin Wild, and Professor Giulio Margli. Their talks were related to sunlight in the far distance. And to the speakers of day two, who looked into the different uses of daylight on Earth, culturally, biologically, and technically, with Professor Richard Perez, Professor Harald Buchmann, and Professor Marilyn Anderson. And all speakers of today, diving into daylight's effects at a very small level, molecular level. Professor Michael Wollig, Dr. Sabine Kling, and Professor Greta Patsky. And I would also like to express our thanks to all the moderators, Professor Marcus Calbera, Professor Jean-Louis Scarpesini, and today Professor Bernhard Werli. And furthermore, I think I would like to express our deepest thanks to the organizing teams, the Daylight Academy team, the members of the Velux Stiftung, and the members of the Sense Tribe, which is the consulting organization that supports the Daylight Academy with the event organization. And there is also Marina Rohr, who did all the very interesting, good, expressive drawings for us. And then I would also thank very warmly all the listeners. And I hope that everyone found something new to take home. And I hope that everyone enjoyed it. And that is, I think we close the Daylight Events Week from this year. Thank you.